Hi, welcome back. In this video, we're going to introduce the chain rule, and we're going to do a few examples. So the chain rule is a shortcut for differentiating the composite of two different differentiable functions. So if f and g are differentiable functions, then the composite f composed with g is a differentiable function, and we want to know a quick, easy rule for differentiating it, so we don't have to go back to the definition of the derivative and compute a bunch of limits. So remember, the composite f composed with g means that you're taking f of g of x. So you're plugging the function g of x into the function f and getting a new function of x. So let's illustrate the chain rule with an example. Suppose our outside function is a function of u, and it's just the squaring function. And then the inside function is going to be the function of x, and that's the sine of x. So if we compose f composed with g, that's going to be a function of x, because what we're going to do is plug the function g of x into the function f. So it's going to be the sine of x squared, or sine squared of x. Okay, so that's the composite. We're composing the squaring function with the sine function and getting a composite. All right, so let's illustrate the chain rule with an example, with this example. So if we were to differentiate just the outside function with respect to the inside function, so that would be the derivative of y with respect to u, what we're doing is we're finding f prime of u. So we're just differentiating u squared with respect to u. So with respect to u, that derivative is just 2u. And then if we want to differentiate the inside function with respect to the variable x, we're finding g prime of x, and that's just the derivative of the sine of x, which we know is the cosine of x. So the chain rule puts this together, and it says, look, if we want to get dy dx, notice the dy in the numerator and the dx in the denominator, we can multiply dy du times du dx. And notice something interesting, the du's would sort of cancel. We don't really normally treat these derivatives like fractions, but if we view them as fractions, something interesting does happen. Dy over dx, if you think of it as a fraction, is equal to dy over du times du over dx, and it looks like it makes sense. So in this example, we said dy du was 2u, and we're multiplying by du dx, which was cosine of x. Now, we want dy dx to be a function of x, not u and x, but all we have to do is substitute. U, we said, was the sine function. So we're going to go back to x's by resubstituting sine of x instead of u, because that's how we defined u. So we get 2 times sine x times cosine x. So what we did was we found the derivative of the outside function with respect to the inside function, and then multiplied that by the derivative of the inside function. So we found dy du, multiplied it by du dx, and got everything in terms of x. So let's look at a couple of examples. Okay, so the first example we're going to look at is h of x equals the square root of x squared plus 1. So the function h is a composite f of g of x, where f is a function of u, is just the square root function, and g of x is a function of x, and that's x squared plus 1. So the outside function is the square root function, the inside function is the polynomial. So then h prime of x, using the chain rule, is going to be the derivative of the outside times the derivative of the inside. And notice the derivative of the outside is with respect to u, but we're going to go back to x's at the end. So the derivative of the square root function is 1 over 2 times the square root. The derivative of x squared plus 1 is just 2x. So this is f prime of u times g prime of x. And now, instead of using u, we're going to use x squared plus 1, because that's what u was defined to be. So we have 1 over 2 times the square root of x squared plus 1 times 2x. And this could be simplified a tiny bit. We get x over the square root of x squared plus 1. All right, we don't always have to write in terms of u. We can skip that step, just knowing that we're doing the derivative of the outside with respect to the inside. So the inside function will not change in that first derivative. And so we can kind of skip the u part. So let's do another example. Suppose we want to differentiate y equals sine of e to the x. So the outside function is the sine function. The inside function is the e to the x, natural exponential function. So when we differentiate y, we're just going to write it down in one step. So it's the derivative of the outside with respect to the inside. So we haven't changed the inside function. We're just not writing u. We're just writing the inside function. Times the derivative of the inside function. And in this case, we know that the derivative of the natural exponential function is just the natural exponential function. So we don't have to write the u in our derivatives. All right, let's try more examples. Let's let f of x be 3x to the third minus 5x squared plus 2x minus 1 to the 15th. Now this is a power of a polynomial. We have no way to differentiate this unless we want to use the product rule with 15 terms in it, right? We could write this as a huge product of 15 factors and then use the product rule and get a sum of 15 products. That's a lot of work. But the chain rule allows us to view this as a composite. So the outside function is the power function u to the 15th. The inside function is just that polynomial. So we can differentiate the outside with respect to the inside. That means keep the inside the same. And multiply it by the derivative of the inside using the chain rule. So let's try it. So f prime of x is going to be the derivative of the outside is bring down the 15 and reduce the exponent by 1, right? The power rule. So bring down the 15, reduce the power by 1, but leave the inside alone. So it's just whatever was on the inside stays on the inside. So that's the derivative of the outside with respect to the inside. Then we multiply it by the derivative of the inside, which is 9x squared minus 10x plus 2. I just differentiated that polynomial. And that's it. Just one step. All right, let's try a more complicated one. So in this one, we're going to differentiate y equals 3x squared plus 5 to the third times x squared minus 1 to the fifth. This is a product. The outermost function is a product, but then the inside functions are both powers of polynomials. So we have a lot of layers going on. So let's start with the product rule, and let's just sort of map out what we're going to do. So we're not going to do it all in one step. So using the product rule, we're going to do the first times the derivative of the second, so I'm not differentiating yet, plus the second times the derivative of the first. All right, so now we're going to use the chain rule. So here's the first. We haven't differentiated. So using the chain rule on the second, notice we have a power. We have something to the fifth. So bring down that exponent, leave the inside alone, and reduce the exponent by 1. That's the derivative of the outside with respect to the inside. And then we differentiate the inside, multiply by the derivative of the inside. Okay, so the second term we have just x squared minus 1 to the fifth. Now let's differentiate the power of that polynomial. So bring down the exponent, reduce the exponent by 1. Notice we left the inside alone. That's the derivative of the outside with respect to the inside. Then we multiply by the derivative of the inside. And we might be done, except we might have to simplify. So let's simplify. There's a little bit of algebra involved, and I kind of want to walk you through that. So notice we have a sum. We have a term which is a messy product plus another term which is another messy product. But it's a sum, and so what we're going to do is try to find the greatest common factor in each term, pull that out, because we want to have everything kind of just factored at the end. So let's look for common factors. I see that I have an x squared minus 1 to the fourth in the first term, and in the second term I have an x squared minus 1 to the fifth. So that means x squared minus 1 to the fourth is the highest power of that polynomial that we have in both terms. We also have a 3x squared plus 5 to the third in the first term, and a 3x squared plus 5 to the 2 in the second term. So the highest power of that one is a 3x squared plus 5 squared. We can pull that out of both terms. And then I notice I have an x there, an x there, a 2 there, and then another 2 buried inside that 6. And I don't see anything else that occurs in both terms. So my GCF is x squared minus 1 to the 4 times 3x squared plus 5 squared times 2x. So let's write those down. 2x times x squared minus 1 to the 4 times 3x squared plus 5 squared. So then what I'm left with in the first term, I'm left with a 3x squared plus 5, and I'm left with a 5, and that's it. And the second term, I'm left with an x squared minus 1, and then a 3 times 3, so 9. All right, so now all I have left to do is distribute that 5, distribute that 9, and combine like terms. So I have a 15x squared plus a 9x squared, and then I have a 25 minus 9, so let's write it down. The final answer is going to be 2x times x squared minus 1 to the 4 times 3x squared plus 5 squared times 24x squared plus 16. And that's it, completely simplified, so WebAssign will be happy. All right, that's enough for this video. I'll have more videos with more chain rule examples, so I'll see you all there.